Hello, I'm Kenneth, and I'll be starting this thing called Kattis Saturdays, where every Saturday I hope to solve a few problems and record the process of me doing so. I hope like you or maybe those who are new to CP will be able to see exactly what I do to solve problems, see my thinking process, and then at the end I'll be sharing a solution, my solution of if I do manage to solve the problem, but I won't be sharing the code because otherwise that's like way too cheaty. Yeah. So to start off, I think I'll be doing a few easy problems, and if I've got the time, I'll try a medium. Today I only have like a few, I think 30 minutes before I have to go. Um, so I'll do a few easy, and if I have some more time later on, I'll do medium, and then you'll see like me merge the clips. I'll just get started because I'm wasting your time. Okay, a different problem. I think I'll do that one because it's rated 2.3. Don't usually go for ones because like 1 point something because it's trivial to the point where there's no thinking involved. Okay, so let's copy our template. It's called uh, a different problem. Okay, write a program that computes the difference between non-negative integers. That's I mean, a bit too easy, but um, I guess that's why they call it easy. The thing about cats is some of them are really hard and it has like a really low rating, but some of them are really like this is terribly easy and it's worth 2.3. Are you serious? Okay. So terminate, huh? So while it's not -1, I'll do a res split and change that to an array of integers. Find the two numbers inside and then print the absolute difference between these two. This is correct. Okay, I'll just go through the process. So after I finish solving the problem, uh, you, I would usually copy the sample input, paste it in, and then wait a second. What happened here? I need to return a -1. Why is it giving me this? Ah, whoops, forgot to do that. There. And then you can see it's correct. Yep. And I usually just usually you want to test the sample before you submit your code. So pretty much correct. Yeah. And then we can go for, what should we go for? I think that 2.3 might be a bit too easy. We'll do, you might be asking why I'm solving by I'm solving by alphabets rather than, uh, oh, this is good, rather than um, difficulty. And it's because there's so many easy questions that by the time, uh, that if I sort by difficulty, then I would have to, uh, like the amount of next buttons I have to press until I arrive at a certain difficulty is very annoying. And so Catis, well, you should change how your sorting system works or how your filter system works because it's very annoying to use right now. Yeah. So next problem. An OM partition algorithm partitions an array around a pivot element. It's a three parts. A left subarray equal to fit itself and the rest of anything that seems greater than okay. Algorithm is an integral part of a popular sorting sort. Usually the choice of parts is randomized at the unexpected. Okay. Now the actual job in this problem is starting from an array A that has n distinct integers. We partition array A using one of the member of A as pivot to produce transform array A. Okay, given this transform array A, your job is to count, okay, transformed array. But doesn't it produce, okay, how many integers that could have been count how many integers that could have been the chosen pivot. Okay, for example, then three integers. 3, 4, 8 could have been e.g. 2, 1, 3 to the left. Ah, okay. Got it, got it. So for example, 3 is because everything is higher than 3. Got it, got it. So how to solve this? Okay. So at a certain position, you want to find the max, whether or not anything to its right is greater. Hmm. So this is less than or equal to, but it's unique, so we can do less than. Okay. So we're gonna use, I'll just do the algorithm first, or like program it out, and then I'll explain the solution right after I get it. I'm like pretty sure it works. Second line contains n. Okay, yeah. And then we'll develop this one. So yeah. Bum, bum. Let's do yup. So pref of I is equal to the pref of. Let's actually do the yeah 1 of equals to um that that. Okay, and then do pref of I is equal to the pref plus 1 maximum I. Oh, I minus 1 and error of I. And then this one is just the same thing, but I want to do this and this. Is that correct? 1 plus 1. And just find the max here. But this one I want to find the. Oh no, no, sorry. This one's max. This one's min. Is it inclusive? It is inclusive. Okay. So, um, 2 doesn't count, right? Because it needs to have at least the size of something. Okay, got it. Okay. Null is 0. Check is true. Whoops. Total increase by. Check is the same thing as. What would it be? It would be suf of 1 less than ARI. Less than AR length minus 1. Then you want to check theta of I is greater than ref. That's correct, I think. So if it is like there, then you check if greater than that. Yeah. So in reality, you don't even need this because everything is valid. Yeah, that's right. So there's an edge case. Oops, I forgot output. Um, did I do something wrong? Check is true. Uh, ID is correct. Oh, nans. Why is it nans? I plus 1. It would be 2. It would be then AR length minus 1. Then it would be 0. Ah, it's... Oh, got it. It's that. Is the soft not working? Still nans. Okay. It would be soft of the same index as this minus 1. So AR length minus I minus 2. Plus, so it's 0. Yeah, that's correct. That should work. And boom. Well, 5 is not correct. Ooh, because I didn't do it here. It's supposed to be I. 1? I keep getting this wrong and it's so annoying. The current one would be I plus 1. See, when you try to overcomplicate things. There. So what, yeah, um, pretty much correct. Okay, so the idea behind this one is you're using the two data structures called prefix min array and then suffix max array. So, um, so the idea, okay, I guess use this 8 and then it goes 2, 1, 3, 4, 7, 5, 6, 8. 2, 1, 3, 4, 7, 5, 6. Okay. So you want to count the idea behind this what the problem is asking you is count the number of numbers or to count the number of positions where for some position everything to its left is less than this number and everything to its right is greater than this number. Okay, so if you do it naively, but what I mean by naively is you say, let's say I'm at this position, and to see if everything to its right is greater than this, you check if 4 is greater, then you check if 7 is greater, then you check this, 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 and likewise you check this, this. You're essentially checking, um, for if we have an array size of n, you're checking n minus 1 for a single position. So for uh, position, you're checking, or rather, I'll say you have n minus 1 operations, right? And because you have 1, 2, 3, 4, 5, 6, 7, 8, total 8 positions or n positions, the time complexity would be n times n minus 1, which basically means this is the number of operations you're going to do. And because n can be up to 100,000, when you plug 100,000 times 100,000, 9999999, is that it? Yeah. You have, what is this number? 9 trillion. 9 trillion operations, which is way too slow considering you have 1 second. So how do you know it's way too slow? That's because sort of there's a level of intuition that comes with it, but there's also, as you do these problems, you learn that um, by it's standardized that uh, n operation. So if you look at the algorithm, right, it's n squared, roughly n squared, because or total n squared minus n, but the bigger factor is n squared. So as you do problems, you'll learn that if just by looking at the time limit that they give you, you can find out how fast your problem should be for it to work. Sometimes there are like very tight situations where you need to actually submit it to see if it works or not. But roughly n squared means uh, n has to be like the total number of operations should be around, I think, 1 million. Yeah, what something, yeah, around 1 million. So 9 trillion is way larger than 1 million, so that's not going to work. And um, we need something because if we're aiming for 1 million operations, we need something where we can do it in n operations. So we can solve this entire problem in n operations. And so the solution for this would be to use two data structures called prefix min array and suffix max array. No, sorry, prefix max array and suffix min array. So let's say you have this, right? This number. How can we check in one operation what if this number is greater than all of these numbers? Well, let's start off with to the left. So you'll have A, B, and C, right? So when would A be greater than both B and A, uh, B and C, I guess, and A greater than C? So an optimization you can do here is that A is greater than this is fulfilled. This is true if uh, A is greater than the max of B and C. So yeah, if you think about it, this makes sense because if the maximum between the two is like B and A is greater than B, then A is also greater than C. Just because we already know that B is the maximum and therefore it's greater than any other number, uh, in which case greater than C. So the first idea would be to calculate um, the maximum of all the numbers given the range. So the maximum of the first number, the maximum of the first two, the maximum of the first three, and so on. And this is what we call a prefix max array. Yeah, because prefix basically means the start, and we're sort of starting, like taking the prefix of this entire big array. We're just taking the start, and that's why it's called prefix, and max because we're trying to find the maximum. So let's try to compute that. So the prefix max array. So in 2, 1, 3, 4, this looks ugly. 2, 1, 3, 4, 7, 5, 6, 8. The first one will start off with just 2. So the second one is 1. So which one's bigger? The previous one, 2, or 1? So 2 is bigger, so we'll always take the bigger one. And 2 and 3, 3 is bigger, so we do 3, and it repeats. And because 7 is, larger than 5 and 6, we have 7, 7, 7, and lastly 8. So what this tells us is at some position, let's say index 2, the largest number from everything from left to index 2 is 3. So these are the values, right? So just using this data structure, we have found um, the maximum of all the start from the start to some point. Similarly, you repeat this idea, but backwards, suffix min. So it's the same idea, but we start from the start, and then we go from here, and we want to find the minimum because likewise, um, the minimum of everything, as long as A is less than the min of everything, it is less than is less than everything, right? Because you're looking at the minimum of everything. And this property applies across all the different elements. This is like, if you really, I'm not going to get technical into that, but you can sort of understand just by thinking about it, and maybe it'll help if you look through more examples. Mm. So suffix, what you then do is start from the back. So you have 8 is just 8. And then 6 and 8. So which one's smaller? 6 will take 6. 5 and 6. Note that we're not looking at this. We're looking at this compared to this, right? So 5 and 6, 5 is smaller. 7 and 5, 5 is smaller. 4 and 5, 4, 3, 1, 1. Mm. So now suffix min, given, let's say, a position 4, it tells us that from the end to index 4, the minimum value for all these would be 5. And now that we have uh, made these arrays or lists, we can calculate the minimum of everything for any position. This can be calculated in one operation, and this can be calculated in one operation also, right? And so in total, um, I guess I'll see how we use it. So if, let's say we want to check for 4 and see if it's less than all these numbers and greater than all these numbers, what we do is get the prefix max of all these numbers, which is just index 2, which tells us it's 3. And then we want to get all the, uh, get the prefix, sorry, get the minimum value of all these numbers, which tells us that this is index 4. So we check index 4, it tells 5. So then we just compare 3 less than 4 less than 5. It works, so then 4 works. That's how you get 4. And likewise, 3 and 8, that's how you check it. So so you do a for loop, loop through every single position. So if position I, you do a suffix min of I plus 1. Oh, sorry. I'll stick with 4. So for some position I, you do a suffix min of I plus 1, and then a prefix max of I minus 1. And you just want to check if uh, this condition holds. Where I'll just say S gives you, like, I don't want to write, I'll just write it, damn it, god damn it. Suffix min I plus 1, and this one's the prefix max. Yeah, and I guess this is the ARR. ARR of I. So if this condition holds, then you add 1. So it tells you that the position, if you, the partition at I works. So you do a for loop from I to every single index, and you just check the number of positions where this condition is fulfilled, and that's how you get the answer. So I think, should I do one more? Above average? I'll do above average. Okay. It said that 90% of Frosh expect to be above average in their class year to provide a reality check. The first line of standard input contains uh, an integer. The number of tests is as follows. Okay. It's split by spaces. Okay. So you're gonna wait, the percentage of students whose grade is above average. Mean, because it doesn't make sense if it's median. So you find the mean of everything and you just find the number of people, divide it, and then output to 3 decimal places. Okay, um, very like straightforward. Nothing, no tricks, nothing. So start with taking in, is there a test case? Yes, C. Then we have input. Oh, wait, I just realized it needs to be like this. Mm, yeah, whatever, it's fine. We don't need n. So I0, I less than ARR of length, I increase. Start off with 1. AR of I total. Now we'll find the mean and divide. And then iterate. Man, my fingers. I cannot type. Is it just the number of... Yeah, okay. Uh, Drawn to decimal figure JavaScript. Too fixed. It's too fixed, right? Now here's a trick that you you didn't see. I mean, you learned. If any Medium article is what is it? Paywalled or login walled or something, just put 12 feet IO. Amazing website. Very helpful. You should support them if you have money. I don't, so I don't. But yeah, wait. I thought they have a pay. They don't have a donation area. Oh, I guess not. Okay. Yeah, so it removes any paywalls, which is like really nice when you're trying to read stuff, but you know, don't got the money. It's too fixed, right? Let me find Media College. I'm just gonna say too fixed. Too fixed of 3. And what are they looking for? A percentage symbol. Let's make it like uh oh whoops. Let's make it like what the hell is happening? There. Yeah, and that should work if we test this out. Oh, I forgot to multiply by 100. Bam, looks good. And I also forgot, golly me, a percentage symbol. And that is perfect. So I think it's a very straightforward solution. I don't think there's much to explain about this. Yeah, I think I might try one more. Actually, no, I think I'll be going now. And if I have time, uh, okay, I'll be going now, but then I'll return later and then do another problem. Yeah, and I'll just like concatenate these two clips. All right. So right now you should see me cut. Bam. I'm back 4 hours later, which yeah, had a nice dinner. So I guess we'll continue. I realize I haven't done a solution for the last problem, and so I think I'll do that. It's pretty self-explanatory. Um, wasn't Yeah, above average. Okay. So the idea is basically it's a list of scores. So you just find the mean of all the scores. So if you have A, B, C, D, it's just A, B, C, D, divided by 4, and you iterate through um, all the numbers, and check if it's greater than this, and that's basically it. It's a bit simple. So we'll do another one. Alex and Barb 3.3. I guess we'll try this. As for visit dinner, since our cousins passing up to the little card game. The game is as follows. There's a stack of K cards on the table. Alex and Barb take turns taking from M to N cards, beginning with Alex. The first player with no valid moves left loses. Given K, M, and N, determine which player will win the game, provided that both play with an optimal strategy. Okay, this one is, I guess, interesting. Um, so let's see. What? Um, so I think it's okay. Let me think about it. There's a very similar problem that exists where it's you can take up from 0 to 3 instead of like 0 to some number of cards instead of um, like being a range. So the idea or the solution is, let's say um, who's it? Bob and Barb. Let's say Barb picks N cards, right? Or if we can visualize it as these are each like cards, but we'll just make it stacks or something. 7. So if uh, N is okay, so if as long as Alex can make sure, or as long as the last player can make sure that the number is N plus 1 left at the end of the game, hmm then it doesn't matter who takes it first, right? So greater than at least N plus 1. So what would it be? M plus N to, you can pick minimum M. So let's draw some stuff. This, right? So let's say this is, so Barb takes this, then Alex should take this. Basically, they want to make sure that. Oh, but it's interesting because it's not that they can take one. So what's N plus M? Okay, let's play out a situation. Let's say they can do 2, 3, and then they have like what's this? 11 cards. So the best way to win this game would be Alex finishes with this. Let's say Alex starts. So he'll pick a full 3. If he picks a full 3, then Bob will pick a full 3, such that Alex must pick 2, and then Bob will win. So Alex must pick 2, which in case Bob picks 3, Alex can still pick 2 and win. Mm. So this is because we summarize it down to the problem being this. Let's say A and B, right? Then you have, we'll do 7 spaces. Wants to always stay 5. Because n plus m, the minimum minus this. So as long as they stay 5, is that true? They can continuously make it 5. If n is 4, like, okay, n is 4 and then m is 2, then five. Is that the case? No. Yeah. Wants to finish it there. So it'd be 2, 4. So if it's 2, 4, we want to make 6. So let's start with 2, like the most minimum moves. Then the order flips, so that's not good. So it's let's say, um, yeah, it's stuck, which means if Alex does 2, they win because Bob, they reach here, which is they reach 7. Okay, so if it's 4, let's say, then he does plays 2, then Bob will play 4, then he loses, right? So Alex must play 4, or must play 4. So if Bob does 2, then must take 2, and then it wins. Interesting. So let's try to understand why this happens. For some segment, they want to stay 1 outside the range. So Alex ideally wants to say for every move they can counteract it to make it 6. So stay 6 outside of the range, right? So within these 4, 6, and then 6. Or it should, okay, yeah. So if this is m, then wants to say n plus m, and then n plus m, right? Okay. So assuming m is the smaller one, yeah. So that works. So basically, Alex needs to see whether it's possible. Right. Okay, that works. Hopefully, there's no number in the yeah. All right. Rename. Okay. So it's K, M, and N equals to imp get split. I cannot. Something I've eaten has made me type terribly. So 522 gives Barb, and that's correct because it needs to be n minus m. No, sorry, not n minus m. K. That's total this, so minus 1 would be this, correct? Yeah. So k modulo n plus m, right? And then minus m. And so what's the gap left? If left is Uh, that's interesting. Hmm. If the number is between m and n, 1, 0, 1, 0, first, second, first, second, first, second, first, second. That's interesting. Hmm. So if I go first and it goes 2, 1, it goes 2, 1, and at 2 plays, I counteract with 1. It needs to be n plus 1 then. Yeah, minus n. So for instance, this minus 3, or minus n plus 1. Yeah, minus n plus 1. Which means whatever's left, let's start with 1. N plus 1. So this is off limits. And so we want to make this n plus m, right? And then we want them to start. Like, I want them to start. So, is it possible for me to put an n here? Whatever's left, right? Is it if less than, if between m and, then he wins. Or like the person who starts win. Otherwise, right, it basically becomes, let's say it doesn't fit. Or do I want to make this n plus m? Same thing. Yeah, same thing. So to make it like this, how can I take everything up? But this last part can be adjusted, I believe. It can. It can be adjusted from 1 to m. So whatever's left means it's not divisible by n plus m. hmm If it's, then what do we do? That's a pretty good problem. No valid move left, which means you repeat the game like that. This is the simplest solution in that the first player who puts it down wins. But when can the other player win? Well, let's think about it. The other player can win if 1 and 2. So combined is 3. 1, 2, 3, 4, let's say. So the answer is 6. So because of that, modulo 5. Okay, so what if it's only 2, 3, and 4? Which means the first player is guaranteed to lose. Because, okay, what if we make it 7 though? Then B will win. Because no matter what they do, let's say we do 2. They will take 4, so then we are unable to take 1. Which is the same thing as going n plus 1, which is 5. Or rather, it should be n plus m, not n plus 1, right? So it needs to divide by 6. And can he play the 1? Can they play the 1? No, they can't, so they lose. If k m less than or equal to k and k less than or equal to m, or what if it's way too big? So, because they can't play this, otherwise if they play anything else, right, even just stepping within, but even like stepping within this boundary isn't guaranteed for them to lose, because it's not as if they can fill this 5 gap, right? Which means as long as they don't exceed m, no, but if they do m here, like they exceed as little as possible, and they go n, they're unable to do it also. hmm Yeah, so basically that's the idea. Even if they step a little bit, whatever they step in is like adjusted. It's not an immediate loss because it's accounted for by m. It's only immediate loss. Okay, so if it's greater, let's say it's like 5. hmm Then you either want them to take full step in, as long as it's not m, or is it as long as if they step inside, whoever steps inside loses. Yeah, you reserve n plus m for the last one, so you like don't even care about that. Mm. So whoever steps inside, then we'll do a full like uh adjustment such that it becomes n plus m minus 1, right? And so if they move in here, m is 2, take. Anything else, take. Oh, this is 4, wait. So if I did 2, then they'd do 4 and then 1. So if I do 3, if I do 4, they can still, like, because it's n plus m, this is 6, right? So if I do 2, they, I can force a 4, and then they win. I mean, I win. Huh. Basically, can we maneuver this? So this is like the first situation where there's like a guaranteed very easy winner because, yeah, else, then it's something else. Is it Alex that goes first? Yeah, just the name. Else, they aren't able to fill the entire thing. Then Barb's goal is if it's less than, it still works because Alex will just the second player wins. If it's less than, then the second player wins. If left, oh, or so it's less than equal to left. I think I got the solution. So let me see. Uh, if left is less than m, then Barb wins. Because uh, whatever left Alex isn't able to play, so Barb will win. Then the other one is if if the number left is greater than n. So if it's greater than n, it means whatever's left, right? If it's greater than n, if I subtract n and it's less than m, yeah, if I subtract n is less than m, else if I subtract it, then even though it's less than n plus m, I'm able to adjust it. So yeah, let me think. So this is left greater than n. Left minus n is less than m. Uh, then okay, because left minus n is less than like this means no matter what I subtract, it's like one left, and for me to start. So then the second player will win. Whoever lands on less than m will lose. Correct. So then Alex will win. Now if it's greater or equal to m, but it has to be less than. There's no way it isn't. Yeah. Because if this was true, then left would be greater than or equal to n plus m, which isn't true. Because left is less than m plus n. Right, so it's Alex. And this should work. Alex. Oh boy. How does this wrong? 522. So doing 4, there's 1 left, so Barb wins. Yeah. Oh, left minus n. Whoops, there we go. Now it should be correct. What? Oh no, this one Alex wins. Yeah. So wait, the first thing we're checking is if left is less than m, in which case Barb wins. And else if left right, left minus n less than n, then Barb wins. Else if left minus n means it's m or greater, then Alex wins because left is greater. Yeah, this is still incorrect. Why? Yeah, so Barb wins. Or is it a swap? Wait. So if it's less than this, then Alex can control the pace and Alex will win. If it's less than M, then Barb will win. Correct? So I don't see why this is wrong. Oh my god. There we go. It was just the input thing. Yep. And this one, Alex wins. Correct. Our logic should be good unless there's an edge case I'm missing. Nice. Okay. So the idea behind this is a bit complicated. I forgot what the original name is called, but so there are a total of three cases. Um, so let's say you have so you can move from any number from the minimum is n all the way to n, right? And so you have like for the sake of simplicity, we'll change it so it's not cards, but it's like coins or something or points, right? And so Alex starts from the left, and they each take some certain amount until whoever takes the last one will win. So if Alex takes this, then Bob takes this, then Alex takes this, then Alex will win. So yeah, whoops, I think I did way too much. But so how do we calculate this? So the first scenario is Alex is able to control the match entirely, right? And how that's like my first scenario. So I'll say Alex controls. And how this happens is as long as Alex makes sure that it's the distance inclusive of the last one is n plus m, they will win. Because if you say n plus m, right? Um, it means whatever, and let's say Bob starts here. If whatever number Bob takes, any amount, as long as it's less than or equal to, actually no, any amount Bob takes, Alex is able to adjust it like so, and they'll be able to take it. So let's say this is 5, right? N plus m, so it will be 1, 2, 4. One they can do they can pick 1 to 4. If Bob takes 1, Alex can take 4. If Bob takes 2, Alex can take 3. Bob takes 3, Alex can take 2. If Bob takes 4, Alex takes 1. So if Alex manages to make it Bob's turn as soon as they are n plus 1 or Barb's, not I keep saying Bob, as long as they are n plus m points away, then Alex can completely control this, right? And so it repeats for this n plus m. Mm. So if the game starts with Bob and it's like 10 in this example, Bob starts, Alex controls it to make it like n plus 1, n plus m distances away, or a multiple of n plus m, and then Bob does whatever move he can, or they can, but Alex will just control it again. So Alex just completely wins in the case of this, right? So, it's not, but Alex is the one that goes first. It's not Bob. So there's some missing values here, or some extra values here. These values are less than n plus m, right? Because if it was greater than n plus m, we would just repeat it again until the remaining isn't. And so whatever's on the left side, that is, uh, so okay. so we'll remove n plus m's as much as possible. In this case, 5. So we have a 5, we remove the 5. We have a 5, we remove the 5. And so we're left with 2. 2 is less than 5, so we can't take 5 away. So what do we do with the 2? And, okay. So if the 2 is between m, or if left, right? We were calling left. If left is between m and between n, then what Alex can do is just move that, just take these two, and then immediately it'll be Bob's turn. And so Bob does a move, Alex controls it, and then basically Alex controls the game. Right. So if this is the first case, Alex has complete domination or control over the game because uh, they take this first, and then it's game over. So what if this doesn't happen? So this is scenario 2. In this case, left, scenario 2 would be left is less than m, right? So if the number of this is less than m, so Alex can't just like finish it and then move on. She can't just finish it so that it's Bob's turn when they start. So what happens here is because uh, Alex has to now step into the boundary of this, right? Uh, it's the equivalent of, okay, how do I do this? Imagine instead of this being at the start, you move it to the end. So it'll be like this. Um, just for the sake of simplicity. So Alex starts, Bob controls it. Yeah. So no matter now, imagine because Alex is starting, um, let's say like even with this, Alex has to do some move. But now Bob is able to control that, abuse the fact that Alex cannot keep n plus m, a multiple of n plus m distances away. So when Alex starts, Bob then controls it to n plus m. Alex starts, Bob controls it to n plus m. Um, but because the end is less than m, Alex is unable to make any move, and so Barb wins, right? So this is the equivalent of, if that makes sense. This is the equivalent of Bob now controlling, Barb controlling Alex because Alex can't get rid of these two at the end or even at the start. So that's where Barb controls it. So then the last one is where left is then greater than m. When left is greater than, oh sorry, not m, but greater than n. In this case, uh, what happens is, let me think. So we can subtract n from left, right? And so what will be left? What will be left is some number of points. So originally, let's say there's some. This is so messy. Originally, there are some number of points, like that's left, and then we remove n from it. So there's some points left. Okay, and so are these points? So here, so you have to think about this. Because this is the control part, right? So whoever starts from the control part, which is like here. So if Bob starts, Bob will lose. If Alex starts here, Alex will lose. So they want to avoid starting this. So Alex takes this or some yeah, Alex takes n or we'll remove n for now. So what's left is uh how do I explain this? I guess the first condition we have to look at is, yeah, okay. So is left, what is the number left here? N minus 1, is it greater than m? or is it less than m, or or is it somewhere equal, right? You have to remember that this is not true, or rather, uh, sorry, that's wrong. So what from our condition here, we originally we stated that left has to be less than m plus m, because if it wasn't, then we would just do another m plus m, right? So left is less than, or yeah, less than n plus m, which is the same as left minus n is less than m, which means uh, what we want to find out of like what value this is. So okay, let me rephrase. Left minus n gives us whatever remaining value this is, and this value is less than m. So it's the equivalent of the second scenario where they aren't able to remove the start to able to control it. So if Alex removes n points at the start, then Barb is put in this sticky situation where they are unable to remove this, right? And so they have to overstep a bit, or they have to. It's the same as this situation where we move this all the way to the end, and then Alex is able to control whatever uh, Barb does, and so Alex ends up winning the game. So if you want like more proof of this, um, I guess like if we go back to scenario two, you have to really understand this. Having two at the start is the same thing as having two at the end, right? Which means the second player keeps on. So let's see, the first one, the first player does whatever move, then the second player controls this move. So first player does whatever move, second player controls it such that the last two are completely unremovable. Same thing here. Once Alex makes it so whatever is starting, whatever points are left are unremovable, then Barb will lose because same thing if we remove just from like here, we have proven that if this is unremovable, then whoever starts loses. And so if Alex makes this unremovable before they get into the n plus 1 business, then Alex will win. Yeah. And so that's the basic idea. Yeah, and that's how you solve it. The explanation took longer than I thought, but yeah. So that's about it for Kattis Saturdays, at least for this week. Yeah, I hope you've learned something, and if you want an explanation of the how this read line stuff or how my template works, please feel free to ask me, and I'll reply. But yeah, see you next week. Bye bye.